Okay, great. Charles, hello. Hello.
Good.
Yeah.
Have you up? Semi-topologies and semi-frames for distributed heterogeneous consensus. And Murdoch, Jamie, Gabbay will talk, please.
Thank you. Thank you, Christian. It's hello, everybody. Hello. Hello at the back. Isn't it great to be here? And it's great to be speaking to people who know better than I do what a quorum system is. This is such a treat. So thank you, Juliana, Christian, for organizing the event and for inviting me to speak. I'm absolutely delighted to be here, and I'm delighted we can all be here together. If you have any questions, the procedure is to put up your hand and ask. I've traveled across the world to be here in this room so that you can understand. Please feel free to ask questions. I don't care if I don't reach the end of this talk. That's not an, I know all the stuff in this, so, you know, that's fine. So a semi-topology, I'll just give you the definition. It's a non-empty set of points and a collection of what I'll call open sets, such that the whole space is open and any union of open sets is open. Hands up if you've seen a definition like this before somewhere. Hands up if you've never seen something like this before. Now you're yanking my chain there, Christian. So the definition of a topology is exactly like this, except that the intersection of two opens needs to be open. So this drops that condition. So that's a semi-topology. And topology has been around for quite a while, even longer than blockchain. This is a thing. And I claim that this definition of semi-topology, it abstracts FBQSs and permissionless frame-prone systems. And when I gave this talk to an imaginary audience practicing, somebody said, but they're not precisely the same. And yeah, they're not precisely the same, but there's a close correspondence. And broadly speaking, every time I say the word open set, if you translate that to quorum, you'll have the right idea. And if every time I say a closed set, you think of a fail-prone set, again, you'll be in the right ballpark. Any questions so far? Cool. Okay, great. Yes? Christian.
Microphone. What about finite and infinities here? Are you considering infinite sets?
So the definition admits an infinite set. Yeah. Yes, definitely. And you know what? Thank you, Christian. This is not in the slides, but I just want to tell you, did you know that in a permissionless system, you can't enumerate the system? And what do we call a set that we can't enumerate? Right, at least infinite, right? And by definition, a set that cannot be enumerable is unenumerable. And in the presence of, I'm good, right? I mean, this is making sense, yeah? And in the presence of latency, it's worse than that, because at least with omega, the smallest, so fair enough, sorry. We can't enumerate the network in finite time, but with latency, we can't enumerate it at all, because no matter what we do, we might discover a whole chunk of universe that has been there all the time. We just hadn't heard about it yet. So in fact, it's not just that infinities are possible, but in some sense, they're built in. P is morally uncountable, even if it's finite, because we can't ever write an algorithm that depends on enumerating P in finite time. Thank you. Does that make sense, Christian? Okay. Thank you for
Jimmy,
that. Sorry?
Just a small note before you continue. You said closed set is fail-prone set, but I think it's probably what people before called a kernel or a blocking set, just so that people are not confused.
Thank you. Okay, good. We'll come to, yes. Okay, we'll see blocking sets in a minute. And yeah, okay, good. Thank you. So here's a difference between topologies and semi-topologies. If this were a topology, then singleton 0 would have to be an open set, because 0 here has these two open neighborhoods and we could take their intersection. But we all know that the intersection of two quorums need not be a quorum. So in semi-topology, a point may have multiple open neighborhoods that are all minimal? Hands up if that makes sense, please. Hands up if you've lost me. I should say, okay, what's not to understand? Okay, take your time. So this is a picture of a semi-topology. 0 has 2 open neighborhoods. And in a topology, their intersection would therefore be open, so there'd be a single least open neighborhood. But in semi-topology, we just don't have that restriction. So 0 is permitted to have these 2 minimal quorums, if you like. Yeah? Yeah, that's right. I said, translate the word open to quorum and everything will make sense. Yeah? Good. Thank you for the question. Now, let's just imagine some participants following some out. Hello? Yeah. They're following some distributed algorithm, and we'll call it S, which by no coincidence at all is the first letter of the word stellar. And we're going to say things about the behavior of this algorithm without even knowing what the algorithm is. And I come from a mathematical background. I love it when you can say things about a system without even knowing anything about it. That's, for me, that's the ideal situation. So we can talk about quorum provision, right? Which just says that this algorithm will only progress P if P has a quorum with it. Hands up if that makes sense, please. Don't be shy. And hands up if it doesn't make sense. Oh, okay. Yeah, so this is my understanding of how these systems work, that a quorum is a set that can locally progress, make a transition. So if a quorum gets together and says we are in agreement on some value, then they can locally take the next step in the transition system. So what I'm eliding here is the whole business of slices and communication. So I'm happy with that. Yes, that's more precise. So I'm not claiming this is sophisticated, but I'm claiming that it's some abstract notion of what's going on. Okay? Happy to discuss further if you need me to rephrase the intro of my papers. Thank you.
We have a question here, Jimmy.
Please.
What does it mean to progress P?
Again, so my intuition is, okay, let's suppose that we all want to vote on when the next AFT is going to be, HTDS is going to be, right? So we could all get together in a room and make a majority vote, and then we all agree. But what could happen is that a majority decides where the next HTDS is going to be, and they communicate amongst themselves to make that decision. So they have progressed, and the rest of the room might not have heard yet.
Okay, so each participant here has some state, and that state can progress from.
That's how I think about this. Yes. Thank you. Any more questions? Okay, good. Now, if you've done a course on topology, then you may have seen the Hausdorff separation condition, which is that any 2 distinct points have disjoint open neighborhoods. This is a Hausdorff space, right? 3 and 2 are separated by A and C, 0 and 1 are separated by A and C, and so on and so forth. It's a nice Hausdorff space. Note that this is definitely a semi-topology. It's not a topology because in A intersection D is not an open set, but that's fine. So that's a Hausdorff condition. And I draw your attention to the fact that the quorum intersection property is precisely the negation of Hausdorff. Quorum intersection for 2 points says that they don't have disjoint quorums. Hands up if that makes sense, please. Hands up if I've lost you. Okay, thank you. So that's what quorum intersection is. It's not Hausdorff. and a space that satisfies quorum intersection. Well, I call P and P intertwined and write that two bracket symbol when they are not Hausdorff with respect to one another. And I'll call the set that's pairwise intertwined, I'll call it transitive. And I'm just going to tell you a lemma. And if you don't see why it's true, that's fine. But I mean, it can be proved that P is transitive if and only if you have kind of transitivity for for intersection. So if O intersects P intersects O primed, then O intersects O primed. For all opens O and O primed, then P is transitive. That's just a fact. So the in-quorum intersection property means precisely that P is transitive, which is just a fancy way of saying that the space P is not Hausdorff everywhere. May I move on to the next slide? Oh, I'll just mention topologists have a word for this. They call it hyperconnected. But I'm not going to call it hyperconnected because that's misleading. In topology, hyperconnected is a very strong property. In semi-topology, hyperconnected splits into 2 or 3 slightly different property, and being intertwined is one of them. So intertwined implies hyperconnected in a topology, but it is a distinct property. So let's look at some examples. I claim that in the top left, in that semi-topology, points are intertwined only with themselves. I'll just check that 1 is not intertwined with 0 because 1 has an open with 1, 2, and 0 has a singleton open. So 1 is definitely not intertwined with 0, and it's easy enough to check. And the right example is a bit more elaborate. If I had the time, I'd set it as a puzzle, but I'll just tell you that the middle block, -1, 1, 2, and 0, they're all intertwined. And that's non-trivial because -1 kind of morally doesn't know about 0. 1 and 2 know about each other. They share a minimal open set, but -1 and 0 are a bit more distant, but they're guaranteed that they are intertwined. And I'll give you a definition. A topen set is a transitive open set. That is, it's an open set, all of whose points are pairwise intertwined. And because of the lemma I mentioned before, it has this beautiful transitivity property. If O intersects T intersects O primed, then O intersects O primed. And there's another lemma, which is really easy to prove, that a union of intersecting topens is topen. And from this, we get an immediate corollary that any semitopology will partition into disjoint maximal topens. If we think of a topen as like kind of a mini quorum intersection universe, then what I'm saying here is if you take a random any semitopology you like, it will spontaneously partition itself into little quorum systems with a quorum intersection property. And you can prove that just by pushing around the algebra of topens. It's a very simple result. Plus some isolated points, which I will come to next. But a punchline is, I'll say it now, that what this means is, if you're a point in a system, you want to know if you're in a topen. Because if you're in a topen, you are in a fully intertwined space that can make progress. Fully intertwined because it's transitive, and you can progress because it's an open equals a quorum. So you want to know if you are in one of these areas of good behavior, if you're in a nice neighborhood, or maybe if you've made some friends with the wrong kind of point, and maybe you're an isolated point. And if so, can we categorize what different kinds of poorly behaved points there might be? And the answer is yes. I won't have time to go through all of this in this talk, but I just want you to know that it exists. And I'll just mention very briefly that quorum provision corresponds to continuity. I won't read this slide. You can read it later if you're interested, or drop me an email. But for me, that's important because continuity is a thing that existed before federated consensus. It comes from topology and it corresponds to something that is useful in the field, which to me is an indication that there is a useful correspondence here. So here are some classifications. Call a point P regular when P is in its community and the community is topen. And the community of P is the topological interior of the set of points that are intertwined with P. The same thing, it's the largest open set contained in that set.
That's the standard definition from topology.
So here, let's look at the set on the top right. Intertwined of 0 is -1, 1, 2, and 0. You do the calculations, it'll work, I promise. Okay, so that central block thing, if we take the largest open set contained in it, we'll get -1, 1, and 2. But not 0. So 0 is on the boundary of its community. It's on the topological boundary. It's not in the interior of its community. So 0 is not a regular point. So if you are in this system and you're 0 and you check your local neighborhood, you might realize, oh, I'm not regular. This may be bad news. Maybe I need to change my quorum slices, right? Whereas if you're 1 or 2, you're sitting pretty. You're inside a topen. It's a nice neighborhood. You can leave your bike propped up by a tree and no one's going to come nick it or something, right? So, and this is just a classification. It's a bunch of definitions. P is regular when its community is topen. P is weakly regular when it's in its community, but its community is not necessarily topen. It means what it means. We'll see examples. And we'll call P quasi-regular when it has a non-empty community. And these are all interesting because they give different degrees of guarantee of good behavior, which turn up in the maths. But the bottom line is that we want the whole universe to consist of regular points. That gives the best properties. So if we go back to that partitioning result I mentioned before, what I'm really saying is that any semi-topology will partition into disjoint topen communities consisting of regular points plus other stuff. Of course, I'm running out of time, but that was... oh, thank you. Thank you. So here are some pictures for you to enjoy. I'll just do this, okay? I'm just going to do this. So this is a topen set. All open neighborhoods, all opens intersect. This satisfies quorum intersection. All the points are regular. We're golden. This is a good place. Here we have 2 singletons. So 0 and 2 are trivially topen because they're singletons. 1, however, is intertwined with both 0 and 2. In fact, 1 is weakly regular, right? So if I discovered that I was 1, I might say, well, you know what? The problem is that I've got both 0 and 2 in my quorum slices. Maybe I need to revise that. So I could get blocked. If 0 decides true and 2 decides false, then 1 might get stuck. We've considered this before. We've looked at this. This is a really interesting case. If you check the definitions, this is... there are no points here that are even quasi-regular because things are only intertwined with themselves and singleton 0 is not an open, so the community of 0 is in fact empty. And there's actually a theorem that's very easy to prove that essentially Hausdorff spaces consist of non-quasi-regular points. For example, the real line treated as a semi-topology is a really bad semi-topology. Nothing is even quasi-regular, which I think is hilarious because when I learned topology, I was taught the real line was kind of the R2 is the canonical topology. And it makes a really bad semi-topology because it consists of lots of points that are separated from another. And that's not what we want, right? We want this thing here. And this is a nice example. I'll just tell you that star is quasi-regular. It's intertwined with 1, but it's not in the community of star is actually singleton 1. And this is nice because star, it's only intertwined with 1. So it's interesting because this guy can simply make progress by doing whatever 1 does, as you see here. I'll move on. Right, so for the rest of this talk, I just want to mention some other things. Oh, it's in the slides, but I should mention this is all joint work with Giuliano. So I'll mention some other things that we've done. So there's a field of point-free or pointless topology, which treats topologies as algebraic structures. And you can take that and give semi-topologies the same treatment. And this is actually, it's interesting because the algebraic thing that corresponds to a semi-topology, which I call the semi-frame, because there's frames and topologies, so semi-frames and semi-topologies, it's a complete semi-lattice. So that just means that you have unions, right? Least upper bounds with this compatibility relation, which corresponds to do these sets intersect? I can see the eyes glazing over here, which is fine, right? But the reason this is important morally is that I describe semi-topologies as topologies without the condition that intersections of opens be open. Now, if you say that to a pure mathematician, he or she will say, okay, well, that's just a up semilattice, big deal, right? Because you just take unions, right? That's what an up semilattice is. That's false. It's an up semilattice with a compatibility relation. So for me, the purpose of building this duality result was to understand what semitopologies are abstractly. So they're not, from this point of view, they're actually generalized topologies, because in topologies, you have a intersection which has to be in the topology. In a semi-frame, you still have this notion of intersection, but it's generalized to just observing whether it's non-empty or not. So let's talk about the logic, and then I'll basically stop when I run out of time. Let's look at this space here, and let's consider a partial function f mapping 3' to bool. And bool is a discrete semitopology. So let's send 0 to false and 2 to true. And as I noted, there's nowhere for 1 to go. 1 can't map to false because that would be discontinuous, and it can't map to true. And you know what? If you don't see immediately why that should be, I'll just tell you that's how the definitions work. So in fact, the only continuous functions out of 3' to bool are constant, which basically means that 0, 2, and 1 would all have to agree. So as far as functions, continuous functions to bool are concerned, 3' behaves like a singleton semitopology, like there's only 1 point. And what this tells us is that if we want to build a logic for talking about semitopologies, it can't be two-valued, because the natural thing to do to build a logic is to consider continuous functions to bool, right? That's what logic, two-valued logic is. You get truth values. So that won't work. But that's a feature, not a bug, because in fact, 3' itself is what's called the classifying object, which is really a fancy way of saying that the set of continuous functions from S to 3' does determine S. So, for example, here, if we have a partial function sending 0 to false and 2 to true, 1 can map to both this intermediate value. And out of that, we can pull a paraconsistent modal logic for specifying properties of distributed systems, and blow me down, it actually works. This is not obvious. But what we can do is we can actually write down predicates that say, am I a regular point? Or what is my community? And then you see the wonderful thing about logic is it's computational. You can take a predicate and you can feed it to a SAT solver, right? You can literally just say, solve this. And if you find a solution, that means the predicate's satisfiable. So there's a whole computational engine that comes out of this observation, which I don't have time to show you, but there's 110 pages of mathematics online here that will spell it out. So I'm more than happy to take anyone through this in as much detail as you like. Just, give me a call. I phoned my father this morning and he said, why can't I see you? I can't see your face. I said, I'm phoning you. He said, phoning? Yes, a phone call. He said, not video. I said, no, the old fashioned way. I'm phoning you. And he said, oh, that's why I can't see you. Oh. Yeah, so this is it. I claim this is a natural notion of truth for semi-topologies, and thus by extension, this is a natural notion of truth. This is a logical system you need for distributed systems. It's a claim. Feel free to refute it. It has 3 truth values: true, false, and both. And the justification for that is that Boole does not classify semi-topologies, but 3 does. And here it is spelled out, the open and closed sets, but it's this thing, which is actually one of the first semi-topologies that we built. It was born in New York. Okay, here's some truth tables. I'll wrap up. So, in summary, Gabbay and Lohse have a theory of point set semi-topologies, and here's a link to that. And we have a corresponding point-free theory of semi-frames, and here's a link to that. We're working on a paper that builds the 3-valued paraconsistent logic. The material is there. I'm fitting it into a coherent narrative. But one thing that's really nice is that SCP can be viewed as solving a horn clause theory. The quorum slices, SCP's quorum slices correspond to horn clauses. It's logic programming. This Stella is distributed logic programming. And you can write down these clauses, and I mean they make perfect sense. It just works. And the paper is in preparation. So, semi-topologies connect heterogeneous consensus and the kind of pure maths that I studied as an undergraduate via topology. Semi-topologies are a new thing. They haven't quite, that precise definition has not appeared before. It's a great source of new ideas in both directions. Topological constructs translate to interesting things in systems and vice versa, right? The distributed systems are a source of new ideas for topological definitions, which I certainly would never have thought of. And they connect nicely to logic. Thank you very much for listening. Welcome questions.
I have a microphone here. Yeah, thanks for the talk. I don't know much or anything about topologies or semi-topologies, but I'm given the impression that they can be used for, like, to model spreading of knowledge, or have different parties who is connected with whom. Has it ever been used like that? Does this make sense to you? Because you talked about communities, about being irregular, meaning being outside, so you don't get information of the community. Like, it does sound like a social thing for me.
So thank you very much for that. Giuliano and I have chosen words to suggestively, obviously. I personally have also been speaking with social choice theorists. And indeed, there are correspondences to social choice. For example, social choice has a notion of a winning coalition, which corresponds to the notion of quorum in this community. I don't like to call it a winning coalition. I prefer to call it a progressing coalition, because in social choice theorists, they're still centralized. They think of, you know, you count up the votes and then you decide who won, right? But you've picked up on a vibe that's quite deliberate. When we were building this, we weren't just looking at distributed systems, we were also looking at voting systems. Having said that, I will say that this thing, it's just a mathematical definition. And one of the beauties of topology and semi-topology is you're free to interpret it in many different ways.
Thanks a lot.
Thank you.
We have a question on Zoom.
Yes, go ahead on Zoom.
Yes. Hey, Jamie, it's me, David.
Hello, David.
So I was just wondering, so let's see how I should phrase this. Can processes reason about missing processes in quorums?
I'm not sophisticated or knowledgeable enough to know what a missing process is.
Me neither, in that sense.
Okay.
It's just one that's not included in the quorum. And
Sure.
maybe because what I've seen, so your last slide about the two-valued logic, there is a paper called Wanted, Dead or Alive, which actually is a three-valued logic about reasoning about crashed agents or agents that just can go offline. And I was wondering if this could be applicable, or like, just, do you think that... In
fact, you're picking up on something real there. So it's not something that we've thought about specifically. I should mention, just for the record, that there's clearly so much that could be done here. So the amount of stuff that hasn't been done vastly exceeds what we have actually looked at. But just to address your question, the logic can reason about the semi-topology that it's in. So as things stand, you can ask questions about, you know, can I see a process with a certain property? That's not a problem. This is a vague answer, but still. But the other thing I want to mention, David, is why stop at 3 values? The addictive thing about paraconsistent logic is that you always want more truth values. And 3 is actually the edited version. When we started, there were 4. And the 4th truth value represented not present.
Ah, yes.
Yeah. So B, if I vote B, then I'm not abstaining, I'm actually voting for true and false. That B stands for both. But there's another natural system with a B and an N means I'm abstaining, or I'm not there, or I'm not present. And I'll just plug this even more. There's a well understood theory of these systems that we can just take off the shelf. I got 3 off the shelf. So the short answer to your question is I'd say strongly, yes, probably. We haven't built it, but the tools are there already. Does that answer your question, David?
Yes. So basically, interpreting your system epistemically should be doable.
Yes, exactly. That's a beautiful way of putting it, yes.
Interesting. We have to
Thank
cut
you.
it short here, perhaps.